Okay, so Liam, we're doing this thing. I can't repeat everything, but I'll repeat the definition at least. Um, so we're trying to prove this theorem. If alpha is a reduced quadratic irrational, then its continued fraction is purely periodic. Okay. And the point of this theorem for us is to get that the square root of n has a essentially periodic continued fraction, and we use that periodicness to prove that it's a solution to Pell's equation. Okay.
Alright.
Okay, which words do you want reminders? Do you know what the definition? Huh?
No, the quadratic irrational is just the square root of an integer that's not another integer, right?
It's not quite. It's a root of a quadratic equation with integer coefficients. So it's of the form like a plus root b on c, where a, b, and c are integers. A
Right.
minus root b on c, you know?
Yeah.
Okay, reduced means alpha is greater than 1 and the other root is between 0 and -1. Okay. And purely periodic means that the numbers that occur in the continued fraction, they all just repeat again and again, yeah? Does that make sense?
Yes.
Okay. Okay. Now that I'm thinking about the argument, I have some questions about it that maybe you guys can help me with. Let's just do this. Okay, okay. Let alpha be a reduced quadratic irrational with conjugate alpha prime. So the conjugate is the other root. This is the other root. Let's write a x squared plus bx plus c equals 0. Which a, b, c are integers and alpha is a root. Yeah. Actually, we don't even need this in brackets. We should probably just have this as a sentence. Since the roots are invariant under conjugation. Okay. So maybe we need to write, instead of alpha is greater than 1, we need to write, or we want to write, that alpha is equal to the fraction. So a plus square root of n over, maybe we want this to be b. B plus the square root of n over a. Okay. With conjugate alpha prime equals fraction it's now b minus the square root of n over a. Okay. Okay. So now what we do is we show that if we write alpha equals a1 plus 1 on alpha 1 to start a continued fraction. So a1 is the integer part of alpha. Then alpha 1 is also a reduced quadratic irrational. Is also a reduced quadratic irrational with of the same form as with the same form as in it has the same square root n. With the same n. The square root. And can be written with the same n, the square root. It's kind of confusing what I'm trying to state. It's also in a reduced quadratic irrational with the same n in the square root. Okay. So we use the quadratic equation. So a times a1 plus, so just do this thing here. Squared plus b that plus c equals 0. Okay. Yeah, multiply by alpha 1 squared and rearrange, get, okay, I don't know how many steps we can save here, but basically this alpha 1 squared. So this will become alpha 1 plus just 1 squared. And here, so you get a c alpha 1 squared for sure. So something alpha 1 squared. Yeah, so can people tell me what these coefficients are? We can check them together. alpha 1, something alpha 1 plus something equals 0. So what's like the constant? It's a 1a Is it plus a? That's weird. What's the alpha squared term? It's a1 squared. A1 squared. Plus c. Plus c plus ba1. And what about alpha 1? So alpha 1 is 2a1, 2a1 plus b. Huh. No way, it's just 1. It's just a. Alright, do people agree with this? Get this. Hmm. Wait, I feel like our reasoning is a little bit more straightforward. Hmm. And the conjugate thing doesn't seem to rely on this. Do we really need to do this? So what's the alternative here? So the alternative is, because we did this, but we didn't really need it. Well, I don't know. So we have like b plus root n on a. Okay, I guess it's not clear what the expression is. So it's like a1 plus. So then it's b minus a1a plus root n on a. I'm just trying to think which one's easier to do because this one doesn't make as much sense. So this is 1 over like a on that, b minus a1a plus root n. And you want to times this by minus root n. And that becomes b minus a1a squared minus n. Okay. This is a b minus a1 a squared minus a root n. Okay, so this is a little bit of a problem because a seems to divide, there seems to be a timesing root n here. And then it doesn't seem to be. So how does it work? So then b squared, so a needs to divide b squared minus n, is that right? Yeah. Oh, but a does divide b squared minus n. Wait, I kind of like this better. What do you think, guys? The a does divide b squared minus n, yeah? Well, I mean, a squared divides b squared minus n, so a does divide b squared minus n. Maybe that's like a more number theory approach. Yeah, I guess this is the one we originally were going for, but we kind of looked at the book. Yeah. Okay, let's change to this one. I like this one better. So then you get the thing of the same form. Okay. And it's root n. So is it negative or plus? We have a plus or minus. Guess it could be negative. How do we say it's negative? The bottom is negative. This is supposed to be greater than 1, right? Assume a is positive. Get b minus a1a minus root n. So b minus a1a, is that negative? Maybe this is a problem here. How do we show it's positive? How do we show b minus a1a is negative? So for this to be negative, that means a has to be greater than a1a has to be greater than b, you know? a1 is greater than b on a. Okay, so the integer part is a1 greater than b on a. I think so, because we need the b minus root n on a to be between 0 and -1, right? So we need the a1. Wait, what the hell? Doesn't make sense. Yeah, can we complete this, people? How do we do this? We just need to show that. Do we need to show it's negative? So a is positive. Do we need to show it's always a positive root n? Oh, wait, actually, the first number, can the first number be negative? So this number here, if we're assuming this number is positive, b minus a1a squared minus n. Do we need it to be always positive? I mean, it has a positive root. But how do we know it? Actually, even in this approach, how do we know that? So we know that the thing in the square root is the same, but we don't necessarily know the sign is the same, right? So, right, so if we look at the book, we know the thing inside the square root is the same. So that's the calculation here. Where is this? So it's not, or maybe this proof isn't complete, huh? Is it not complete? Okay, so what does it mean to solve for the positive square root? Um, do we know it's okay? Maybe we do know it's positive, right? Because a1 is smaller than alpha, so we know that alpha 1 is positive. But how do we know there's a negative square root? Sorry, how do we know there's a negative root of that equation? Yeah, like how do we know that P1 minus root D on Q1 How do we know that's negative? Hmm. So that's the question right now, guys. So how do we know that the other square root is negative? Or how do we know that's not the one we want? So the B is um the P1 is the same as the previous B, but you subtract something. So this is negative. The Q1 the Q1 is the same as the other stuff, the A, but you times it by A squared. E plus BA1 plus C. How do you know that's positive? Huh, that's interesting. You're just subbing in A1 into the equation and timesing it by 2 to get Q1. So A1 is a little bit less. It's a little bit less than the root. So if something is a little bit less, and you send, that doesn't make sense. So A is positive. So one of these square roots is here, and the other one is like there. You know? This is the one that's like B plus root n on A. This is B minus root n on A. And if you just sub in A1 into this, it feels like it should be negative. Yeah. Oh, wait. So if alpha is greater than 1, then the other root is negative. Okay. The other root is negative. Oh, how do you get that? Assuming A is positive. So assuming A is positive, we don't know if C is positive or not, do we? Or actually, we do know. Actually, we do know C is. Yeah. So actually, yeah, we're given the other root is negative for alpha. Yeah. So if alpha is greater than 1, we're given that the other root is negative. So C is negative. Okay. So we do know that. But now, if we know alpha 1 is greater than 1, How do we know the other root is negative? A1 is at most 1 less than alpha. It is between the two roots. Yeah. Yeah, so A1 is somewhere here. Wait, so if you have A1, wait, so if you sub in A1 to the equation, you should get negative, right? So is Q1 negative here? No, I feel like the more carefully you read this, the more mistakes you can find. I think this is a good exercise though, because if it's in a book, it's got to be right, yeah. So you just trust it, but you don't need to. It's maths, right? So Q1 suddenly turned negative, huh? I mean that's good for the other argument. Okay, so if Q1's negative, then you need like P1 is negative. Then you need the negative root D, right? Hmm. Is P1 like basically diffing? Basically diffing. Um, hmm. Oh yeah, you substitute A1 into the derivative. Uh, with the negative. The negative. Okay, so some super sus stuff. So their proof is not even correct anyway. Now I'm tempted to include it. Okay. Yeah, but I think you can fix that because then Q1's negative. You know that P1's negative, Q1's negative. So then you take the positive square is actually minus root D, and then the Q1 becomes positive, P1 becomes positive. Yeah, exactly. It should be negative square root D, yeah. Yeah, but once you take the negative square root D, it all works out. So it seems like you can even show, wait, so you can even show um, that the P and Q's stay positive. But then, hold on. Did we solve the problem that it was actually the positive square root? How do we know it's not the negative square root? So how do we know it's not the... Yeah, how do we know that's not that solution they put there, even though it's wrong from context? How do we know that one's negative? Is P1 greater than negative? Wait. So that becomes yeah, is 2A A1 plus B. Yeah, so when you sub in A1 into the derivative, is that going to be greater than root D? Why would you sub root d into the derivative? Why the value? Why would subbing it into the derivative compare with the root d? Yeah, so I guess the question still is like, how do we know there's only one positive square root? I guess we need to prove that anyway because, oh, wait, we can just do the other argument first. Hold on, let's just do the other argument first. We're gonna do it anyway, and we can use that to show the other square root is negative. Yeah. Okay, I think we can complete their proof, but it'd be nice to come up with our own proof. So the question is, so the proof that we want is like b. Why is b minus a1a squared minus n? Why is that negative? Okay. Okay, but their proof we can continue. We can finish their proof right now. So we start here. Okay. So this shows that alpha 1 is a quadratic rational. Maybe that is direct as well, because you need to show it is the root of a quadratic. Okay, this shows alpha 1 is a quadratic rational. By design of the continued fraction, it is clearly greater than 1. We show that its conjugate is negative and greater than -1. No? So write alpha 1 equals alpha minus a1 reciprocal. Okay, so we write alpha 1 equals 1 on alpha alpha 1 equals 1 on alpha minus a1. And the reason this is kind of nice is because conjugation is an automorphism. Okay, so it's a field automorphism. So kind of like complex conjugation, right? Since conjugation is respects algebra operations. Similar to complex conjugation called a field automorphism. I guess we say field just because we got reciprocals. Otherwise it's a ring. We take the conjugate of both sides to get alpha prime equals. Is Liam on his phone? Who's on your phone right now? I'm trying to imagine what it's like when you guys are at home. Is it more focus, less focus? Oh, there's definitely some kind of focus. Yeah, I kind of like that sometimes because you know, like people when they want to like they always want to do face to face or like when they do Zoom, they always want you to have like the video on and stuff. But I feel like when you kind of turn off a lot of the other channels, it does give you some kind of extra focus in the channel that's on. Kind of like when you're reading a book. It's like you basically turn off everything but your imagination. Okay, so alpha 1 prime equals 1 on that. Okay. We know from assumption that -1 is less than alpha prime less than 0. Which shows that both alpha 1 prime is negative and a1. So a1 is going to and alpha 1 prime is greater than -1. So this is where like a1 is greater than or equal to 1. Hence the other root of the quadratic for alpha 1 Yeah, it's actually, yeah, it's the quadratic. The quadratic is written with a negative starting point, which is weird. A was positive to start with. Yeah. Yeah, you can tell because it's meant to be negative here, right? But it's positive, so. Since the other root of the quadratic for alpha 1 is between 0 and -1 is required. Hence the other root of the quadratic for alpha 1 is between 0 and -1 is required. So that actually shows the other root is negative, right? So alpha 1 is the positive root of the equation. Found and by the quadratic formula. Yeah, I would kind of like to finish off the other proof though. I wonder if anyone could find that for homework. But then it doesn't quite show it's the root of an integer quadratic equation, but that's sort of obvious as well. No, we did show that. Okay, so alpha 1 is the positive root of the equation found by the quadratic formula. Alpha 1 equals fraction what is it? Maybe it's a good time to write the discriminant at the top. We also see that the discriminant is b squared minus 4ac, so it's that squared minus 4, this is something a equals b squared minus 4ac, which is the same. I think it is just equal to n. So what's b? B is 2a a1 plus b minus, and then a is a1 squared plus b a1 plus c. So is that true? So when you square that, you do get 4a a1b. That's 4a1b that cancels. You get 4a squared, a1 squared. Oh, this is meant to be squared. And that cancels, and then you get a b squared which stays. And you get a 4ac which stays. Yeah. So then this is equal to um so something minus the square root of n over 2 that. And this is minus b. Was b positive before? I guess we don't know if p is positive, that's the thing, right? A is positive, A1 is positive. But we seem to know that this is negative. Yeah, because we know A is positive, yeah. We know A is positive. We should log that A is positive, yes. Maybe if A was negative, it would work out. No, but then C would be positive, and it would still change sign. Okay. You can't avoid this. Which equals square root of n, equals 2a1 plus b plus the square root of n on what's 2 times a. Why am I doing this? Let me just copy that. Okay. Hence it is of the form b plus square root of n on a for a positive and um b is integer. Okay, we now show that in this form, b is an integer. That there are only finitely many possible values of a and b. Finitely many possible values of a and b. Okay, but this is not hard, right? This is definitely downhill from here. Um. Okay. So what can we say? So we we have assumed that so the conjugate is between -1 and it's negative. You know? So b plus square root of n over a is negative. And it's a minus. Which means that b has to be less than the square root of n. Okay. And we also know since there are only finitely many values of b, okay, we have also assumed that a b plus square root of n is greater than 1. Which means that a is greater than, what the, a is greater than, a is less than b plus square root of n, which is less than 2 times the square root of n. Okay. Hence there are only finitely many values for a. Since there are only finitely many values, if we continue this process, to generate more terms in our continued fraction, we will eventually have to repeat Okay, so my question now is, so we're almost at the end. My question now is, can you explain to me why repeating terms proves that it's purely periodic? It sounds kind of stupid, doesn't it? Like, so repeating terms, I guess, why does it show it's purely periodic? Like, how do you know? Hmm, I guess, how do you know the first one will repeat? You guys understand my question? Hmm. Oh, wait, so the book actually does prove this. To prove 2, we shall now show that AK equals AL implies, huh, yeah, so, I guess technically we can stay a bit over a little bit, right? Because we don't have no longer have the travel time. Hmm. Well, I would really like to finish off this. Like, how do we know it's periodic from the beginning? Yeah, that's the final boss for today. Yeah, like it's obvious once it starts repeating, like the whole cycle repeats, right? That's part one. I guess. So what's it trying to say? Like you have some continued fraction, right? So like alpha equals a1 plus 1 on a2 plus 1 on a3 plus 1 on, and let's say it just starts repeating, right? a2 plus 1 on a3 plus 1 on, okay. You want to prove that, what's it saying? You want to prove the thing before the a2 is also a3. Can you show a1 equals a3? Oh, so this is where that other lemma might come in handy, because it reverses it. So you have the negative reciprocal of the conjugate is the reverse continued fraction. So 1 on, so you can assume that, I guess, negative reciprocal of the conjugate is, so this is at the moment a1, a2, a3, repeat, right? How do you reverse that? It's not really reversible, is it? That even makes sense. Wait, so we don't necessarily have its reduced fraction. Like, it's the reversed if we don't know it's purely periodic, or do we always know that the negative conjugate is the reverse fraction? Huh. Alright, so this says, okay, so this part's pretty straightforward. I'm trying to show that alpha. So we have alpha k minus 1 equals ak plus 1 on alpha k. So remember the alpha is the tail starting from the position of the subscript. So alpha k minus 1 just starts one entry earlier. Okay, so if you take the conjugate of this, you get ak plus 1 on alpha k conjugate. It's the same for L's. Okay, so I don't understand why they're taking the negative reciprocal, but we are at some point. We do kind of know the negative reciprocal should be the reverse. So I guess the motivation for the, like, you know, if you want to go in reverse, then the reverse continued fraction is a good way to go. So rewrite this as that. Negative. So okay, we put on the other side to get that. And okay. So this is beta k equals ak plus 1 on beta k minus 1. Since the a's are reduced, okay, are they reduced? Yes, we proved that they're all reduced. 0. So then the betas are all between 1 and 0. The one on betas are between 0 and 1. So that means AK is the integer part of beta K. So that is a continued fraction. So this is continuing a fraction for beta. So if beta K equals beta L, then AK equals AL. And beta K minus 1 equals beta L minus 1. I think that's the end of the proof. Does that make sense? I guess the motivation is the fact that the negative reciprocal of the conjugate is the reverse continued fraction. But we're kind of writing it so that we're kind of writing it so that if we can conclude beta K minus 1 equals beta L minus 1, then we're done. And basically, knowing that A, K, and AL are the integer parts of beta K and beta L, and beta K and beta L are equal. So once all those things are equal, the K minus 1 and the L minus 1 are equal. Okay. I don't know what's going on over here, but I feel like we already concluded that they're equal. Yeah, like you proved that the repeat actually started one earlier, so it has to start at the beginning for it not to start one earlier. Alright. Do people understand that? I guess if we have another 7 minutes to maybe type this up. The first term must be the first to repeat, okay. Wait, what exactly is it that we proved? I'm confused now. What is it? Alpha k minus 1 equals alpha l minus 1. Ah, okay, so the cycle. Okay, it's not quite has repeated already. It's more that if the kth term repeats, then the k plus k minus first term is the same as like the 2k plus first term. Yeah, kind of. So you're basically getting another continued fraction where the sequence of parts is reversed. Yeah, so I get okay. So maybe I can replace it more. So show that if the kth term repeats, so then it goes in a cycle until the kth term comes. So like, okay, maybe I should say this better. So we show that if the k term repeats, so the kth term repeats every period, every L. I don't want to use the letter L. If you use the kth term repeats every P terms, then we show that the k minus first term is the same as the k plus p minus first term. Yeah. And the k minus first term is okay. So if the kth term repeats every k terms, that is maybe not even term. It's like alpha. Um, alpha k equals alpha k plus p. Yeah. Then alpha k plus p minus 1, k minus 1 is equal to alpha k plus p minus 1. Okay. So Yeah. We could say L is equal to K plus P to make it look more like theirs, but okay, so the motivation of this argument comes from knowing that the negative reciprocal of the conjugate of a reduced of a purely periodic continued fraction is the reversed continued fraction. That's beta sub I equal negative alpha sub I. So we write alpha, so alpha k equals, so alpha k minus 1 equals a k plus it's a or a k minus 1. So maybe it's a k minus 1. Doesn't really matter. A k minus 1 plus 1 over 1 on alpha to the k. That's the definition of alpha, basically. Okay. Then we write this in terms of beta. So now it's going backwards. Beta k. So beta k minus k. So negative of 1 over alpha conjugate is equal to a sub k minus 1 minus alpha. So alpha k minus 1 conjugate is 1 over beta k minus 1. It's actually plus because it's already negative, yeah. Oh, maybe I'll just write that. I'll write 2 lines here. K minus 1 is equal to a sub k minus 1 minus alpha k minus 1 conjugate. Okay. Similarly for beta sub k plus p minus 1 plus p equals a sub k minus 1 minus beta k plus p minus 1. Alright, we're almost there, people. Okay, so the point is the beta k is equal to the beta k plus p, right? So, okay, this should be an alpha k plus p minus 1. Yeah. Okay, so we need to justify why the A's, sorry, this is the A's are equal. Okay, we know the betas are equal. We need to justify why the A's are equal. If the A's are equal, then these betas are equal, and we get the result. Okay. We know that beta k equals beta k plus p, and we show that a k minus 1 equals a k plus p minus 1. Which allows us to conclude that beta k minus 1 equals beta k plus p minus 1, and hence alpha k minus 1 equals alpha k plus p minus 1. To do this, we show that a k minus 1 is the integer part of beta k. Okay, this is where we can write like respect a sub k plus p minus 1 beta k plus p minus 1. Okay, so how to show that? To show something's the integer part, the something equals an integer plus something. So you just got to show that that other something is less than 1, right? If they're all positive and stuff. Yeah, so the negative reciprocal of something which is between -1 and 0 is going to be positive and bigger than 1. So it's going to have an integer part. So beta equals integer plus something, okay? So we just got to know that that something is, positive and less than 1, okay? It suffices to show that 1 over beta k minus 1 is less than 1 and it's greater than 0. But remember, it's the negative reciprocal of something, which we know is like a reduced. But beta k minus 1 equals, so the negative reciprocal is just negative then, negative of alpha sub k minus 1 prime, which is, so that was between 0 and negative 1, so the negative of that is between um, okay. So similarly for a plus p minus a plus p minus 1, hence this completes the proof. Alright, what do you guys think? Is that poll still up? Hmm. So if it was unclear then, probably unclear now. Alright, time for questions. We've got 2 minutes for questions. Let's see. Was it Liam that put unclear? Hmm. Okay, so maybe as for homework, because I think the point of this was to see what happens for the square root of n, right? So for homework, maybe you can apply this theorem to show what the continued fraction for the square root of n is. Hmm. Alright, does anyone want the recording for this? Oh, are people still alive? There's still someone not voting. Maybe that's Liam is not voting. Hmm. I've misjudged him. All right. Okay, yeah, so if people want to tell me what the square root of n is, that's you can put it in Discord or whatever, okay? Um, does anyone want the video? I mean, if not, I won't take I will take my time, but if someone wants it, I'll try to get it up quicker.